Assalamu alaikum. Bismillahirrahmanirrahim. In our today's talk, will be covering another important topic that is to find out the numerical solution or approximate solution for the differential equations. So here we are going to cover two methods. One of them is the Euler's method, and another auxiliary part of the Euler's method is improved Euler's method. So these are the two methods which we are going to cover in our today's talk. Eulers gave the idea to approximate the solutions of the first order linear differential equations along with the initial conditions. So the strategy which he gave us to approximate the solutions of the differential equations, so first of all we'll see that strategy or theory, and then at the end, as usual, we'll be applying the theory on solving few questions. So here the title of the method is the Euler's method. He solved an equation of the form dy over dx having the general form dy over dx equals to fxy along with the initial conditions y of x0 equals to y0. This is an initial value problem. Okay. In order to approximate the solution of this differential equation, he approximates the solution curve of this differential equation by using the straight lines. In order to understand it, let me construct here a graph, and this is the solution curve which we are going to construct. So this is the solution curve for this differential equation, and the points which are at the two end points, these are basically the end points or the interval points, and he divides the whole interval into the small segments or small sub intervals. Okay, so if we divide the whole domain into the smaller sub intervals in the form of if I start from x0, the next will be x1, x2, x3 and so on up to xn. So we have divided the whole segment which starts from x0 up to xn and divided into the smaller segments in the form of x1, x2 and so on. The first point corresponding to this initial condition will have the coordinates x0 and y0. Now if I draw a tangent line at this point, suppose this is the tangent line, it is not going to be finished at any place, it is going to be extended to any direction, in both directions, but I keep it up till here. So this is the tangent line which we have drawn here at the point x0, y0. In order to write the equation of this tangent line, because this is a straight line and we know that in order to write down the equation of the straight line we require two informations, the slope and the point. Point is there. How we can find the slope? The slope can be obtained by using this differential equation. If I take this point, so at the point x0, y0, dy over dx will be according to the given differential equation having the slope this one. So now we have the point as well as the slope, then we can write down the equation of this tangent line. The tangent line equation is y minus y0 is equals to x minus x0 times the slope, which is x0 and y0. So this is the tangent line equation which we have just constructed, and when we reaches to this part of the interval which is at x1, if I show it here, so the point corresponding to x1 will be definitely on this tangent line. The corresponding coordinates of this point are x1 and y1. So when this point lies on this tangent line, the equation of this the tangent line equation will change. So here we write down at the point at x1, y1, we get y1 is equals to, if I transfer it on the right side, this gives you y0 equals, this is plus x minus x0 now changes to x1 minus x0 and f of x0 and y0. So this is the so far condition we have. Okay. Now this is the equation when we reach to this point x1 and we got this equation. If we look at this part, this is basically the difference of the two endpoints, the first two endpoints. And generally we show the difference by the letter h, so I can replace it by writing it as y0 plus h times f of x0 and y0. So here you can see, in order to find the value of y1, we are using the initial condition that x0 and y0. Now, if you follow the same principle for the next, if we keep plotting the tangent, now if I plot the tangent line at the next point, it goes in this direction, the next goes in this direction, and keep on drawing the different tangent lines. So these straight lines are now going to approximate this solution curve. Although there is a difference between these, and this is due to the approximation principle, we are not getting the exact solution, we are obtaining the approximate solution, so there will be definitely small or big errors, and those errors can be reduced by keeping your h small, and that is why this method works so slowly, and error can be removed by reducing the value of h. Okay, after doing this, now if we go to the next interval, so according to this equation, we can write down the next equation directly. So the result takes the form y1 h times f of x1 y1 for the second interval. You can see here for y1 we use the previous values which were given in the form of the initial conditions, and we obtain y1. After finding y1, then you can use y1 and x1 in order to find y2. Similarly, the next can be obtaining by using the previous values y2 h times f of x2 and y2. Now if we keep on proceeding on the same lines, so we can generalize it in the form of ym plus 1 is equals to ym plus h times f of xm and ym. So this becomes your first formula, which is known as the Euler's methods formula. So this is the formula we can use it in order to approximate the solutions of the first order linear differential equations along with the initial conditions. The advantage of this formula is, in this formula you can see there are no more derivatives involved. While originally the differential equation is given, and you have to tackle with the derivatives, and it is not very simple to tackle with the derivatives. So in this simple algebraic equation, we can just substitute the values and we can obtain the approximated values very easily. And here the value of m goes on from 0, 1 and so on. So these are basically the levels at which we can find out the corresponding values of y. So this is your first formula. Now we turn towards finding the second formula, and that is the improved Euler's method. So let's start studying the theory of that method. Okay, so here improved Euler's method. The title is improved Euler's method. Now to understand the theory of this particular method, we are again given the same problem dy over dx, and the initial conditions are x0 and y0. Now once again we draw the similar kind of graph, and this is your, suppose this is the same curve which we have just drawn, and the first point corresponding to x0